So I'm going to be talking about the new OpenFabrics Management Framework. We've been working on it for a couple of years now, and things are starting to really move forward on it. First thing I'm going to talk about is the group that's working on it. We've got quite a few people represented here. We've got OpenFabrics Alliance ourselves. We've got people from Intel, including Phil and Richelle, CXL Consortium, DMTF, Cornell, IBM, SNIA, Lawrence Livermore, on and on. So I'm going to go into a little bit of a description. We keep talking about composable disaggregated HPC systems. What are they? Why do we want them? So current HPC architectures, everything is kind of designed to a little bit over-designed in the fact that they put the same components on all the machines, and they have to over-design a little bit to make sure that they can accommodate codes that have different requirements, different types of batch jobs, and on and on. So the composability gives us the possibility of mitigating resource over-revisioning, which helps by reducing energy consumption and also really the price of the machines, and allows us to, with the same money, same footprint, possibly increase the size of the machines. And then we do that by provisioning extra resources when they are needed dynamically. So I took a little bit of this off the DMTF website, the DMTF specs. We've got different types of composable disaggregated HPC systems that are possible. So for instance, we have specific ones that will, we link inside the DMTF Redfish tree. We'll link up a specific block storage device, a specific area of memory on that. We'll do the same thing with fabric attached memory. Constrained compositions are designed to, what they'll do is give constraints, and then those are listed in the DMTF Redfish tree. We want a block storage of this size, for instance, this size but not bigger than this size, or this memory needs to be at this location or whatever. So those are what those two are. And then what we're going to be concentrating on with our with HPC systems, I think, mostly, are going to be expandable compositions where we have an existing chassis. Might be a little bit under provisioned, but we can dynamically add in memory, fabric attached memory, which would be byte addressable memory, or we can add in block storage. You heard Phil's talk earlier about NVMe over fabrics, and you heard the person from CXL Consortium talking about byte addressable memory. That's what those are. And then also you heard earlier CXL3, we'd have, for instance, here's an example of binding a host to a fabric attached memory. I want orange to orange on the left side, blue to blue on the other side. But then we can also subdivide it with CXL3. Host on the orange on the left side going to get a portion of the fabric attached memory on the left side, and then the host in blue gets the rest of it. So now that we got that kind of background, so what does the OpenFabrics Management Framework for Composable Distributed Systems do for us? So Redfish, I'm going to explain a little bit about this composable disaggregated infrastructure as far as Redfish goes. I'm going to talk about disaggregated infrastructure in an HPC architecture. The OFMF architecture, I'm going to go into examples of some use cases we've come up with, and then our next steps on the OFMF design front. So Redfish, representation of composable disaggregated infrastructure. So on the left side of this picture, I took a simple map. I simply take a simple map of what's on the right side. I've got resources on the right side, real resources, and I'm taking them and putting them on the left side. I got chassis, I've got fabrics represented, I've got media controllers, media domains, systems, and everything has a link with more detail or the actual connection information to the stuff that being done on the right. So for instance, endpoints will be attached to memory controllers and memory domains and memory chunks. I've got switches that I've got connections to ports on the media controllers and also to the system and connections on the on systems, so that you can actually make associations, and that's what the OFMS is all about. It's making associations and keeping for whole systems. It's like a central repository for all that. Again, here's our simple diagram. This is what it looks like in real life when we gather data. On the right side, you'll see I've done a curl command in Bash, and I've pulled back NVMe over fabric. I've got a fabric collection here. I've got 2 fabrics on the system. I've got NVMe, and then I've got Ethernet. And I can drill down from there, and I can actually add in if another fabric's added, for instance, CXL in this case, I do a post, and the post would be done by a fabric agent, and it would fill in the details. For instance, in this case, I said, I've got a CXL fabric, and I can add that in there and then add in the details on it, down line on it. Same thing here. So I've got endpoints here. So I took the NVMe example here, and I've got an initiator, and it tells me I've got a network controller, I've got an address for that. It's an Ethernet address. It tells me the port number and tells me the number of links. And that goes, again, corresponds to whatever is in this mapping on the left. Again, port linkages. I've got, if you look here, now all of a sudden I've added in, I drilled down even further, and on the right side, and I've got listed, I've got a volume that I'm attached to, and it says, I'm attached to IP attached drive number 1. I've got a volume, and I've got a namespace for it. And the same thing with the drive 2. And those, again, will give you more detail, and then they link back to something in the storage, under the storage tree. So for instance, if I go to the storage tree, on the left, on the right, I would say V1 storage, and then I would okay, I got an IP attached drive number 1, and then simple namespace, and it will have a link back to this endpoint or this connection. Again, just taking that same picture again, for subdivisions, I've got more detail again on the right. I've got durable names. I've got details. I went into the storage namespace. Now I've got names for the namespace. I've got the number of bytes that are allocatable, so I can subdivide off of that. I can provision off of that if I want to. All that details in the Redfish tree. Picture here of that NVMe mapping. I've got storage on the left, and then I've got the tree on the right, the logical device, and I've got a picture really of what's going on inside the machine. And that could be even details on if I got a flapping link in between on the fabric, attached NVMe over fabric, and my fabric's got a flapping link, I'll get details on that. If I have memory come and go, something fails or whatever, I'll get that detail too. So we're in this case, I'm going to go back to where we were talking about earlier with the specific and expandable compositions. Really, what we're talking about, what I just showed you, was both. It's the specific. I've got a specific link assigned, and I have it's an expandable composition. So I take an existing chassis, and I can expand it with fabric attached memory. Let's say I want a lightweight chassis with HBM or whatever, or I want a lightweight chassis with, I've got only a certain amount of RAM on there and I want to run a bunch of containers. I can add in more fabric attached memory to accommodate that. If I want to do dynamically add block storage, I can do that to that chassis too. And then of course it runs through the cache controllers, and it's byte addressable with a block device. Here's a mapping of different examples of a system, HPC system. On the left here, we have Gen Z. We have a Gen Z setup where it goes to a Gen Z switch and fabric attached memory. And then on the fabric attached memory, we have a resource enclosure, and I can subdivide that fabric attached memory on the left side. When I go to the next side, that composed server can also add in GPUs through a CXL switch. You can add in CXL fabric attached memory and GPUs. And then on the right, I've got an RDMA fabric, and that's given me the ability to add in NVMe over fabrics. I've got, in this example, and then you'll see I have in each case, I've got an orchestration service that'll be your fabric manager, and of course you'll have some resources that are dedicated to running the fabric. The architecture. So this is what the architecture of the OFMF looks like. We have on the right side, we have agents, hardware agents that are talking to the fabric. On the last picture, those were the resources managers. They'll talk to the resource manager for CXL, in this case, Zephyr for Gen Z, Slingshot, OmniPath, and InfiniBand. And they'll convert the information back and forth from the OFMF, the information and controls from the OFMF, to the actual hardware. So if I want to, for instance, OmniPath comes up and it says, oh, I've got an OmniPath fabric, it'll take that OmniPath fabric, it'll translate that into Redfish, post all that information over to the OFMF, which is a central repository, and say, okay, here's the fabric endpoints, and make the associations to, for instance, if we have memory on there, or we have another, we want to know what the fabric looks like to other machines, or we want to know what the fabric looks like to provide us with resources like GPUs or whatever, or pools of memory. They'll provide us with, it'll give us all that information as it populates. Everything's done by events. So the OmniPath agent comes up and says, oh, I have a fabric I found. That's an event. Then as it fills in all the details, that's an event. And it goes through the OFMF. And if you're subscribed to the OFMF, it'll give that information over to a composability layer, and downstream from there over to whatever's talking to the composability layer. So the OFMF has a resource inventory, contains the resource configuration, what endpoints connected to what resources, for instance, the fabric configuration, if you have a fat tree or a dragonfly topology or whatnot, who's got the ability to authenticate against it, to subscribe, for instance, to get the information, so you don't have users going on and unauthorized getting the information. We also have access control, and we've got logging. So if we have a flapping link, for instance, on our OmniPath or ID link or Gen Z link, for instance, it would tell us, oh, this is flapping. Let's find something else to use to get to that resource we can. And then, of course, on the left side, we have the composability layer. It's checking the events. It says, oh, I see a new fabric. I see new resources that are available to me. If I get a client that wants to subscribe to resources that fit that category, it'll be able to do that. And if it says, oh, I've got somebody that wants to subscribe to those resources, they want to subscribe to, they want to associate this CPU with this memory block, and it can do that, and it'll propagate again with events back to the right side, and then that'll be the agent will go to the fabric manager and say this is assigned and associated. They'll go back to the right side and it'll associate the memory blocks. It'll report back to the OFM of success or failure, and then that reports back an event to the composability layer so the client can know, hey, it's done, or I had a failure for some reason. Use cases. So we have a lot of people wanting to use containers now on HPC systems. Part of that reason is that it gives everybody that you can give users the ability to have the same environment on multiple machines. There's, for instance, if we have an undersubscribed system, let's say they were using it, they're using their container on a bigger system, and they wanted to port this over to a system that's got fewer resources of a certain type. We can have pools of memory or resources or GPUs or whatever, and we can pull those in as we need to dynamically and subscribe this. In this case, the container engine is going to go over and say, oh, I need containers for each compute node, expand that compute node resource to include more memory and associate to these CPUs. And if you look over here on the right side of this picture, you'll see I have a blue CPU going through the CXL switch. That's associated to CPU 1 on container 2. And the same thing with, I've got another stripe for the orange one. Let's say container N, CPU 1 is attached to a portion of the memory on the CXL switch on the right, and it's actually bridged across through a Redfish Swordfish link. It's associated with a Redfish Swordfish link, and it's associated through a fabric. So in another case, we would have like an expandable we'd have, like, for instance, BGFS is a dynamic on-demand dynamic file system. Currently, to run that, you take out some resources out of your compute nodes, and that becomes part of the parallel file system. Would be better is to compose a system, again, by expanding those nodes and associating memory to improve. They'll give you the resources, and since it's an I/O system, there will be less. It won't be so intrusive on the system as far as resources. So you can leave that memory alone inside the machine and expand the memory that you need with NVMe or Fabrics, for instance. Next steps. So right now, like I said, we've started really moving now. Things are really moving forward. We are working to add events. Again, that's how we make notifications of changes to the whatever our system is. Network fabrics, for instance, are detected. Any hardware changes, any associations that have been done. Excuse me. So we're working on that right now, getting all that hashed out. And then we're working on getting mock-ups for CXL Gen Z RDMA. And then we're working on new, and Richelle and Phil know this, but we're working on new redfish tree cleanup and stranded resource notifications. We're going to have to put services into the OFMF. When we lose Chris, if we lose a fabric or lose an endpoint, we want to drop the association with that, and we want to try to find a different way to get to that resource if possible, or cut that resource out so people don't try to use it, and then clean up any resources that we aren't using. And then we're working on development of a reference fabric agent framework. We want to have a framework together so that people, when they, vendors and groups can build, for instance, InfiniBand, they can build an InfiniBand fabric agent and know that this is going to work pretty close right out of the box. They can put their secret sauce in there or whatever they want to, but they'll know, they'll have some assurance that that works with the OFMF. And then also the same on the other side, on the left side of that picture I showed earlier, we're working on building a reference composability manager framework. We'll have a framework built, and again, whoever the client of the OFMF is, they'll know that kind of work that works out of the box with the OFMF. They can add whatever secret sauce they want to add in to their framework composability managers, and have that knowing that it'll work out of the box. And then of course a fabric attached memory framework as well. So we want to have, and same with the NVMe, we want to know that when we do the associations, that'll be done. So that's all being done too. And then one thing that we were brainstorming about too is we don't really have any assurance yet. We don't have the composability manager done yet, but my understanding is, and Doug can straighten me out on this if this is wrong, but as you add and subtract memory dynamically, the OS does not like that. With these new CDI systems, that would be something that we need to kind of hash out with the OS providers. And then we're looking for a new fish name. The OFMF is a great name. We're working with Redfish and Swordfish, so we want to have a fish name. So if anybody's got a great fish name, that'd be for the OFMF. That would be, we could take that in a revisement. Does anybody have any questions?
I was gonna say it's exhausting to say OpenFabrics Management Framework all the time too.
Yeah.
Okay. I have a really difficult time with just saying OFMF. It's a tongue twister. So a much better fish name would also just be easier to say.
Especially when you're referring to the body that works on it. So the OFMF WG.
Yeah, by a vowel, please.
Okay, so do we have any questions for Michael? I think quite a few folks online have been working on it, so maybe familiar with what we're doing. Okay, so thank you, Michael. And you and I
All right, thank you.
this afternoon.